check, 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 check. Okay. We're okay. This is example 2.8. So it is from the textbook. How many of you have opened up the textbook so far? Oh, none of you. Okay. So we do most of the important problems. So they don't have no body. Yeah. But figure 3 shows a wind turbine generator used for taking mechanical energy and producing electrical energy. So what we're going to do is use some of their assumptions. Now, looking at this torsional, this bar right here, I'm sure that there's probably some twist going on in that bar. But we are going to make some assumptions. The book tells us that J1 is rigidly attached to gear 1. So all of this turns the same way. Same thing for the generator in gear 2. So we don't have to look at the shaft, any kind of bending there. We're just going to assume they move together, all the same theta. So we've just got one theta 1 and a theta 2. And we're also going to use an ideal gear. They're also saying the mass of the gears is negligible compared to the weight of the other components. And we want to derive the mathematical model. What's our starting point? Breathe. Okay, thank you. This looks kind of complicated. I know we did a rotational problem last time, but a gear, wow, okay. Let's go for it. So I take my breath. We can do this. What do you think the order of the system is? I guess how many objects are we looking at that can move in total? There's really two objects. So we've got J1 and we've got J2. And how many degrees of freedom does each of them have? Two degrees of freedom? Like it can move two different ways? Backwards and forwards. Now, is backwards and forwards 2 degrees of freedom or 1 degree of freedom? It's a question for all of them. For the mass, if we think about, x-axis, that's still just 1 degree of freedom. I can move back and forth on that. Same thing with this. As I'm rotating, this has 1 degree of freedom, which is theta 1. And we also have 1 degree of freedom here. So we are going to have a theta 1 double dot. There's going to be acceleration. There's going to be acceleration for J2. And so in total, I've got, this is second order, this is second order. So we just add them all up. This is fourth order system. So each of them has a degree of freedom. Now, if I move theta 1, does that affect theta 2? Like if I move J1, is J2 going to move? Are they dependent on each other? They are. So this might change down the road. We may be able to combine some of the things going on. But we'll get there when we get there. For right now, I've got two objects, each 1 degree of freedom, second order. Okay. Body diagrams. Unless anyone's got questions. Body diagrams. So like any of these problems, I like to draw where I'm going to be looking from. I'm going to be looking from the left-hand side this way when I set up my system. Now you could look at it from the back side. That just kind of flips all the directions. But looking from this direction, I'm just going to draw them as circles. This is J1, and this is J2. And so I'm just going to follow the directions they gave me. Theta 1 is positive clockwise. But for the generator, they said theta 2 positive counterclockwise. There is a relationship through the gear. I want to give you a chance to try to put down some of the torques that you think are going on here. Some of them are pretty easy. They're given by the problem. But there's other torques going on. There could be some friction. There's gears interacting with each other. How is that going to show up on the diagram? So I'm going to give you a little bit of time, a couple minutes. I want you to try to add these torques onto the diagram. If you got any questions, just let me know. Both of these have friction. Then lastly, T arrow, T-gen. Those are my two givens. Now there's bearing friction for the turbine. Which way should the bearing friction? It will be a torque between the body and housing. So there's some kind of viscous friction going on that's going to oppose the motion. Which way should that point on J1? There's two options, clockwise or counterclockwise. Counterclockwise, yes. In. Izzy, why'd you chose that direction? Positive theta, awesome. It is not based on T arrow, very good. This is based on what is a positive direction. If it moves positively, if it moves clockwise, the friction should oppose it. Similarly, for J2, we also have a viscous friction. It's a different coefficient, B2. Which way should that point? I thought, yeah, this way. Clockwise? Clockwise. Yeah, it should be clockwise. Because just like I said, like she said, for the first one, it is not based on the torque here. It's all based on what's a positive motion. So if it moves positively, counterclockwise in this case, we should oppose that motion. Does that seem weird to you? It could seem weird, absolutely, because you're like, wait, I thought this torque was going here. Isn't it going to move negative? Might not. Based on all the torques going on here, it could be moving positive and negative at different times over a length of 10 seconds. It could kind of oscillate between the two. But we just want to be able to always go against positive motion. If it goes negative, that's going to flip the sign. It's going to flip the direction of this arrow for us. And then lastly, right now I have nothing connecting J1 and J2, but obviously from the picture, they are connected through a gear. How is it going to work? Let me draw this out a little bit from the side view. So I've got this large gear here. So here's J1, and it's going to spin this way. If this is positive, theta 1, and it's going to contact this smaller gear. This is J2. So that's going to spin it this way. Now there is a contact force between the two. So if I try to spin this, there's not only friction that's going to oppose it, there's also a gear in the way. So that when these teeth mesh up, there's something in the way. So we have to be able to turn that as well. And so I like to look at it kind of at this zoomed in perspective where that's my contact point. I'm going to have a equal and opposite contact force happening between those two teeth. So J1 is going to experience that force as well as J2. It's an equal and opposite force. I'm going to call it contact force. That's where the teeth contact each other. So both of these are going to give me torques. They're not going to be equal torques because we know that torque is equal to force times distance. In this case, it would be radius. And the gears have different radii. So the one with the larger radius is going to have more torque. Okay? Questions? Oh, wait, we haven't put it on our diagram. How would we put this on our diagram? Like, which way is the contact torque going to be acting on J1? It tries to spin, it runs into that smaller gear tooth. It's going to be resisting the positive motion. And so therefore, we're going to have a contact torque like this. I'll call it TC1. So that's based on the contact force pointing to the right times the radius. So now we can see from J1 that, well, to get this thing moving, T arrow has got to overcome not just the friction, but also that contact torque at the gear tooth. If I don't have more torque than that, it's not going to move. Now we go to J2. So if I'm looking at my diagram on the right, I have this contact force pointing to the left. That's going to kind of turn J2, and so we're going to have TC2 point this way. A gear is not the same as a spring. I know that with the spring, it's going to be equal and opposite. We did that torsional spring last time in class. With the gear, they actually point the same direction. So if you notice, both of these are going counterclockwise. And what I'm doing is I'm transferring, some of that power. I'm transferring the speed, power, force, torque from this first one to the second gear. And that's the way that it's going to look. So gears different than springs. Question? There are no questions. Everyone understands. Okay. Now we got to start defining these, but first we're going to do inputs and outputs. So I'm going to look at both sets of systems. So we're going to create a tic-tac-toe. I got inputs, outputs. We're going to look at J1 and we're going to look at J2. What would you say the input is for J1? T arrow. And then for J2, we got T gen. So there's usually some kind of external torque to allow us to create that electrical energy. Outputs, just like we've talked about, they should be displacement. So theta 1 and all its derivatives. And then for J2, we're looking at theta 2 and all its derivatives. And do we have anything else affecting any other inputs? Theta 2 is also an input for J1 and vice versa. They affect each other. So if I am spinning one of these, theta 2 affects theta 1, theta 1 affects theta 2. Okay, why is this important? Just trying to, again, it's okay if you don't get everything in the inputs and outputs. What I'm trying to do is figure out when I get to my final equations, what's on the left-hand side, what's on the right-hand side. I'm going to be looking for two different second-order equations. So the combination of those. So just trying to, this is all just a roadmap of doing all the steps and trying to then put all that information together to get it to the end. Questions? Got it. Just had a student join who knows what's going on. Okay. Definitions. This is a rotational problem. The first thing I'm going to start off with is sum of torques equals J theta double dot. Okay, if I go back to my free body diagram, I need definitions for everything except, some of the given ones. So I don't need to define T gen. I don't need to define T arrow, but I do need to define the other four torques. So both of the friction torques and the contact torques. So let's start with the easier ones. Let's do friction. So we got a TB1 and we got a TB2. Now, for a rotational problem, this is on the equation sheet, which I would encourage you to use as you're doing the homework. The equation is, we have our B times delta theta dot. So just like with springs, I don't want to forget about the delta because sometimes the delta is extremely important. I gotta figure out what that delta is. Now, in this problem, do I have a delta? Let's say for TB1, the friction is acting between J1 and the housing, which is fixed. So do I need a delta? No delta. I mean, we could say that it's like theta 1 dot minus 0. So it's just B1 theta 1 dot. The wall doesn't move. Same thing for the other one. It is strictly looking at the velocity of the generator. There's no delta, there's no relative velocity. So we've got those knocked out, that's good. Just be really careful when you're setting these problems up. Make sure you get the subscripts. So these thetas matter. I can't just put theta because I've got a theta 1 and a theta 2, right? So got to make sure we keep those labeled throughout. Questions so far? Okay, let me go back here. That's my friction. Next up is the way that these relate to each other through the gear. We've got our forces, and so we got to define TC1, TC2. Now the torque is pretty easy. For any kind of force away from the axis of rotation, that's right here. So the torque is just going to be equal to that contact force that's felt at the teeth times radius. So we're going to use that for our definition. The force is going to be the same for both of them. We're just got a different radius. So we've got TC1 is equal to the contact force times R1. TC2 is equal to the contact force times R2. Based on the picture, which torque is greater? Larger gear, right? The more radius you have, the more torque you have. Which one of these has a higher speed? Rotational velocity. Yeah, the smaller one is going to be moving faster. And that's why, they set it up this way. They want the generator to spin more than what the turbine is, because that's where the energy creation is happening. Good? Okay, you might remember when we talked about ideal gears that we can, look at the torque from one to the other. Like, for example, this is the same contact force. So really, I could say that TC1 is related to TC2. We're going to get there because there is a possibility we can put some of these things together where, T2 is related to T1. That is a way you can kind of approach the whole problem, starting with the free body diagram. But I like to kind of split it up, have different torques right here where I've got the same contact force, and then I can combine things at the end. Okay, so we've got everything defined. Now we're going to put our two equations together. You're all good? Okay, so let's start with J1. We're going to do sum of torques equals J1 times theta 1 double dot. This is why it's second order. I'm going to have acceleration. So this is where I go to my torques. I go to my diagram. Which torques are positive for J1? T arrow is the only positive one. So we got T arrow minus TB1 minus TC1. Now we're going to put our definitions in. So this becomes B1 theta 1 dot. This one becomes contact force times R1. And so I've got my thetas on different sides. I want to get all of my thetas together. So we're going to add that friction theta 1 dot over to the left-hand side. That becomes J1 theta 1 double dot plus B1 theta 1 dot equals T arrow minus contact force times R1. Our first equation. Basically, the way that J1, the turbine, is going to move, it's going to be the difference between the torque from the wind that's causing this to spin. So that minus the contact force, the torque from gear 2, because if those two things are equal, it's not going to move. But as the wind speed picks up, as it starts to spin, then that difference gives me a positive value where I can see acceleration and velocity. You know, is this a good equation? I have a negative in there. Did I do something wrong? No, it's on the input side. The output side was theta. This is all positive. It's stable. That's good. Okay, let's go to J2. I got sum of torques equals J2 theta 2 double dot. I go back to my equation. And which torques are positive? Wait, what? TC2 is positive, counterclockwise, yes. So just be careful. It's all based on the axes. So this is TC2 is positive. Then we got subtract Tgen, subtract TB2. Now we put those definitions in. Contact force times R2 minus Tgen minus B2 theta 2 dot. And just like before, we want to get all our thetas, all of our outputs to the same side. So we get J2 theta 2 double dot plus B2 theta 2 dot equals contact force R2 minus T gen. Two equations. So just like we said, we were looking for two second order equations. So here we have two second order equations. It's a fourth order system. We've got stable systems. And it looks good. Now, can I create a transfer function out of each of these? I mean, if you look at each one individually, they have two inputs. So each one has two inputs. That's not going to work for me to create a transfer function. But you know what's coming? There's more we can do. I know that the contact force is the same in between these, so there is a way to group those together. I know that theta 1 is related to theta 2. I know that if I turn one, I'm going to turn the other. So it's really not two sort of independent systems. We can really treat it as one system where we can look at everything going in together, J1 and J2. We can look at T arrow and T gen to create one equation. That's what we're going to do right now. First, what I want to do, something we can do. Now, in the homework, it specifies a lot of time what the output should be, like what our transfer function should be. We're using displacement theta as our output, but when I'm looking at this equation right here, oh, you couldn't, oh, wow, okay, gotcha, okay, wow. Because I don't have a theta right here, I can actually change a little bit of the goalpost, like what's our output? If you're looking at wind turbines, do we think like we care about exactly what the angle is, or is it easier to kind of maybe treat it looking at what the velocity is at any point in time? That's something we could look at. So like if the problem says change the goalpost, change the output instead from position to velocity, this is what it means. I know that theta double dot is acceleration. Theta dot, which is radians, by the way. Sorry, radians per second. So theta dot, that's radians per second. We can change that to omega, which is radians per second. And that means that theta double dot, which is radians per second squared, would be equal to omega dot. So I can simplify my system. Instead of having two second-order equations, I could have two first-order equations. Instead of looking at what is the actual position of the turbine at any point in time, we could look at it in terms of speed, velocity. And so I can take both of these and change them, simplify them a little bit. So we put it in terms of omega. So we have this equation, and we've got this equation. So, oops, cut off that dot. Now what we have is two first order equations. I now have a second order system where instead of looking at position, I'm looking at velocity. So what is my velocity of the system at any point in time? We can look at either this one or this one, but it's still a little complicated. I still can't create a transfer function from either of those. But I know that all of them do connect in some way. So I'm going to go to the next slide soon, and we're going to try to figure out how to combine these things. How can we put them all together in a way that makes sense? Questions about what I just did? Omega is always in this class radians per second. It's our angular velocity. So we can do the same thing with the translational system. We can change position to velocity x dot equals v. I can just make that quick change. Anytime I don't have, in this case, we didn't have any, zeroth order derivative. We didn't have just a theta by itself. So then we can change it to omega, just simplifying the system a little bit. Okay, so we're going to go to the next slide. We're going to try to figure out how to put these together. So here's my first equation. T arrow. Okay, there's equation 1. Here's equation 2. And this is contact force R2 minus T gen. I want to combine these because I know that they are all connected. The gear, I've got a lot of connections going on. How would you say would be a good way to combine these? Solving for F. Very good. So if I solve for the contact force, we can plug it into the other one. It doesn't matter which one we do. I'm just going to do this one. So FC, contact force. If I add T gen over to the other side, and then I divide by R2, I've got J2 omega 2 dot plus B2 omega 2 plus T gen. And we are going to just plug that right into there. Because I know that the contact force is equal and opposite. And so we can make the substitution. So I get J1 omega 1 dot plus B1 omega equals T arrow minus. We're going to have R1 over R2, J2 omega 2 dot plus B2 omega 2 plus T gen. Okay. Now, I have a really nice second order equation, would you say? Really nice? Maybe? Or does it seem a little bit worse? Is it better to just keep the two separate? Is it better to combine? Because this does look a little bit complicated. I mean, I've got an omega 1 dot, I've got an omega 2 dot. I have two output variables right here going on. It's actually, I don't know if it's better. But is there a way that we can simplify this a little bit more? I mean, obviously, I can add some of this stuff over to the other side. I could get the omega 2s together with the omega 1s, but I still have like two output variables. It's a little bit confusing. We really want to just have one output variable per equation. So is there a way to simplify? Anyone got any ideas? Like if I spin gear 1, does gear 2 move? Like are the speeds related? Are the velocities related? Is omega 1 related to omega 2? Yes, they are. We have the gear ratio N, capital N, that's equal to R2 over R1. So driven gear over driver. It's also related to the number of teeth. Now that also gives us a relationship between the torques. So the larger radius you have, the more torque you have. This is inversely related to the speeds. So the larger the gear, the slower it's going to turn. So based on these relationships, we can substitute out either an omega 2 or an omega 1 using this relationship, because I know that these speeds are related through the gear ratio based on the radii. In this problem, they gave us the radius. And so I can make this relationship. I can either solve this in terms of the turbine speed, or I can do it in terms of the generator speed. I'm just going to pick one. I'm going to say we're going to have an output. Output is omega 1. So as I'm creating the mathematical model, and the homework typically, it's going to tell you what it's looking for, what the transfer function should be. But in our case, I know that there's a relationship here, so I can simplify my system. Instead of looking at both omega 1 and omega 2, we can just look at it in terms of one of them, because I know that they're related. So like for omega 2, so omega 2, if I want to solve it using this, omega 2, I move it over here, and then I multiply both sides by R1, divide by R2. Omega, we can say, is equal to R1 over R2 times omega 1. So for every omega 2 in there, I can replace it with this. It's just related to the gear ratio. But I also have omega 1 dots. Got omega 1 dots. So if this is speed, this is acceleration. The relationship with this is the same exact one as this one. If the speeds are all related, the displacements are all related, then the accelerations are all related. If the speeds are always equal, that means that the change in the speed is also always equal. And so I can take the acceleration, omega 2, I can change all those to omega 1s, all using this relationship right here. Because this goes on, I mean, it's equal to theta 1 over theta 2, also omega 1 dot over omega 2 dot. All of these are equal based on the gear ratio. The more radius you have, the slower it's going to be. the harder it's going to be to accelerate. So this is how I can take this complicated system. I don't like having two output variables together in the equation, but if through a gear, they're always going to be related, just like the torques are related, the speeds are related. So instead of looking at both of them, we can substitute these in and put it all in terms of J1 or omega 1, sorry. Now, I've had a lot of people say, Professor, like it makes a lot of sense when you're doing it, but for some reason when I'm doing the homework, like it's just hard. And the reason is I've had a lot of practice with it, so I can make it look easy while trying to explain it. Okay, I've got a lot of practice. That's what the homework is. It's practice. So it's okay to struggle. It's okay that it doesn't make sense right away. But just trying to, this is a little bit tougher of trying to put it all kind of in the same, because we know that they all move together. We can combine it into one equation. Questions? So we're going to plug them in. So now that I've got my relationships, everything now is going to be in terms of omega 1. So I've now gotten to my first omega 2. We don't want omega 2, omega 2 dot. And so we're going to take what we've got on the right-hand side and plug that in here. We've also got this right here. We can change to R1 over R2, omega 1, and we still have T gen. And what do you think our next step is? We're almost there. We can almost, yes, similar terms. So we've got our like terms, our output variables. They're on two separate sides. I want to get them to the same side. Notice that this is all negative in the brackets. So this is negative. I'm going to add it to that side. I'm going to add this one as well. And so we should be able to get one nice equation. For example, my starting point, I'm going to have J1 plus R1 over R2 squared J2. This is all multiplied by omega 1 dot. So it's a combination, which makes sense. Both of the moments of inertia are going to affect how this turbine is going to move. Same thing for the damping. I've got B1 plus R1 over R2 squared times B2 multiplied by omega 1. So both of the frictions are going to play a role in this. And then lastly, what I'm going to keep on the right-hand side are my inputs. So I do have two inputs. I got T arrow, and I have R1 over R2 T gen. So what's happening with that last term is that we are just using the gear ratio to take whatever that generator torque is and transfer it over to the arrow. So in this case, it's going to be more torque because I have a higher R1 than R2. So the combination, this is my input side, this is my output side. We're looking at it in terms of speed. And now what we're left with is one first order system. So the gear allows us to simplify the system, to take something that's really complicated because there's the contact force in between. It's equal and opposite because the speeds are related. We can take this large system and create this one overarching equation that can model the motion. So if I know these values, I can figure out what the speed is. If I'm trying to figure out what my moment of inertia, how much mass that turbine is going to be, I can easily plug that in to see how that affects what's going on here. What is our motion going to be? We don't want to go too fast. We don't want to kill too many birds, right? We want it to go a little slow, so maybe we add some mass here. We see how that affects the acceleration velocity. Questions? Nothing. Great. I'm going to leave this up here. If it's still not making sense, I'll stick around. Let's take 5. So if you have questions, you can definitely ask it. And then I'm going to have you work on a problem. If you want to pull up your laptops, we are going to use MATLAB for the last section of class. So let's take 5 as 812. So 817, I'll give you a problem and we'll work through it eventually. Oh, you're all over. Well, I'm going to give you a you haven't got it figured out yet. Hopefully you can. Now you work with Reagan. Both work 40 hours or what? You got her the job. She's working part time. You're working full time. No, I just thought she had the same sweatshirt. Oh. So they're like promoting the company, you know? Okay. Yeah. Nice. Yeah. United Front. Now ATD means something very different to me. ATD in my past life was anthropomorphic test device, also known as dummy. But yeah, that, that's what ATD means. Yeah. Yeah. Okay. Yeah. Yeah. Yes. Yeah. Very cool. Part of the homework. It's a simulation tool. We don't do really much SolidWorks in this class. It's more MATLAB based. MATLAB? Really? Trust me. Wow. Make this code for me. You can, uh, oh yeah. So we don't. It would be nice. I mean, I'm right now gonna go through very soon a revision of this class to get many calls, so it's possible that that could be some model. I don't know. I'm not sure. They used to have, honestly, all mechanics robotics. But then it's like, oh, now we have an emphasis. But there's not many people in robotics. So not many people get used. Yeah. Yeah. They don't. Yeah. What? Non-linear? Just a little, but not test one. Test one was all linear. But after that, there's ways that we can linear. Yes, there's no non-linear. All right, welcome back. What I'd like you to do in groups of two is I'd like you to solve this problem. So this is problem 2.4. We want a followable body. You can definitely ask me for help if you get stuck, and I can always check your model. When you are correct, when you're done, you can definitely help other people at your table, whatever. But today's goal is not only to create the mathematical model on paper. The other goal is to create the SimScape model. So taking a look at it, trying to identify, you took the on-ramp, so hopefully you know some of the things you can use here, and I can help you with that. And I'll give you some more information as we get closer. But step one is trying to solve mathematical model for. And if some things are confusing, like the order, or you're not quite sure inputs, outputs, you can always skip some of those parts and just get to, what are my definitions? What do I know to be true? But people claim that they only made it for some people. They were very proud of it. So basically, everybody that has body, yes, body, body. That is one of the outputs. definitely. No, I was a little confused on what's going on. Hey, got lots of time. Time is not the issue. My classes. They should take board games. They want another fun class. How do we do this? How many degrees of freedom do we have? So we have both a mass that can move, and we also have a node, which we consider to be massless, but it also has a degree of freedom. So I'm not looking for one equation. We're going to have an equation both for the node and for the mass. So really I have 2 degrees of freedom, each with their own equation. That's going to affect the order. For your body diagram, you can only put a force on the body if it is in contact, if it's actually acting directly on it. So for my mass, there is no damper connected to my mass. What do you do with that? Yeah. Yeah, some things are explicitly on the Yeah. Not really sure what the order is, so I'm just gonna skip it. Maybe it's fourth, maybe it's second. I don't know. I have 2 degrees of freedom. I don't know. Hey, with your body diagram, like I said, because both of them can move. So here's node. And here is mass. So we need to have both of them, and there is a fourth. In our definitions. Like what? The node. This says that the node is basically a mass with a mass of 0. Just a point. Each of these should have I don't remember. I just know it was Hail Mary. All right. So we have a force here For the spring, did you say the spring was in tension or compression? Or did anyone actually care, or does it matter, or what's going on? Does matter? Is it the spring in tension or compression? Tension. Yeah, it doesn't matter. But if you want it to be in tension, we can say if Z1 is greater than Z2, then we're going to have tension. We have our spring force like this. Now you can go the other way. You can say Z2 is greater than Z1. Now looking at the problem, if the force is my input, I probably imagine this thing starts to stretch. But either way works. Now, which way should the damper point? Opposite the, not the spring. Opposite the positive motion. So if Z2 is to the right, we're going to close it. So for any positive motion, we're going to have a friction. This is how you want to do it. Now, for your definitions, your spring equals delta. Both ends can move. Damper does not. Then from there you can set up the two equations. So once you get to the end, if you want me to check it, I can check it, and then you can move on to the sim state. Yeah, you want me to check it? Yeah. So I just put my inputs, outputs. It's okay if you didn't have all of these. I think just trying to identify, what's going to cause motion for either of these. So in my final equations, these should be a part of my final equations. Have any questions? That was a great time. So it should be a combination. You know. But then, yeah, once you're here, you're gonna do some of for both node and then you can do another equation from that. So you have positive force minus negative force equals, or in this case, zero. I did when we were dealing with like gravity, but you don't always have to. No. Oh, that's what I was. Yeah. All right. Here's some definitions. Obviously, we're going to have Newton's second law. I only have two components. So we've got the spring force, and we've got the damper, which have similar looking equations. Now, for the spring, it all depends on how I drew it. So the way that I drew it is I said that Z1 was greater than Z2, so the spring was in tension. Therefore, for my delta x, because this is between this and this, both ends can move. I'm going to have Z1 minus Z2. Gotta have it. Anytime I've got a spring with two ends that can move, like this, I've got to include the delta. And not that I'm just going to have delta in my final answer. I also don't want that. I want to expand out. What does delta mean? So in this case, to have tension, we said Z1 greater than Z2. So that gives us a positive value. For the damper, it's tied to a wall. The only motion it sees is Z2. So we could write it as B Z2 dot minus 0. That's the wall. So it's just B Z2 dot. So these are the only definitions we need to solve this. I do have two equations. I'm going to do sum of forces for the node. I'm going to do sum of forces for the mass. But when I put it all together, we should be able to get, is it fourth order, second order? I'm not quite sure. We'll kind of figure it out as we get there. Are there any questions? Questions? No questions? Okay, you'll get practice on the homework, especially with springs, just being careful with the delta. So now we get to I can do the mass, sum of forces equals mz double dot. Which z is this, by the way? Because that does matter. What acceleration are we tracking? If I'm looking at the mass. Yes, z1. So on my free body diagram, I have a positive input force. I've got a negative spring force. So we put that definition in. And of course, we want to get our like terms to the same side. So I've got mz1 double dot plus kz1 is equal to force minus kz2. Equation 1. So we just needed those two definitions. Each degree of freedom, I've got my equation, second order. So we're going to go through, we're going to put all the definitions down, and then we're going to do our sum of forces, in this case, for the mass. Oliver? What's that look? You look like I did something wrong. Yeah, it should be positive. You're right. You're right. Never seen anyone mess that up before. And so that is my first second order equation. Then we get to the node. sum of forces. I have m z2 double dot is equal to, I have a positive spring force, I have a negative damper force. Now the nice thing about this is that the m for the node is 0. So actually the sum of forces is going to equal 0. There is no acceleration, there is no mass. So this is going to be k z1 minus z2 minus b z2 dot. And so because the mass equals 0, this is equal to 0. So we can add over to make it a nice stable system. We can add the bz2 dot, we can add the kz2, and this is equal to kz1. This is my second equation. Now, how many of you saw, I've got kz2, I've got kz2, let me set this equal to kz2 and plug it into here. I'm sure some of you, maybe if you got to the end, did you have that desire to, just like in our last problem, try to put it together? Anybody? That's a typical, yeah, like we just saw it done. It's possible. I see we have same terms. The problem is that that would give me a z2 dot and a z1 double dot in the same equation. I do not want to have two different output variables, two different sets of derivatives, because that's not a nice ordinary differential equation. I just need to have one output with derivatives. So we're actually going to keep these separate. Now these are stable, the output sides are positive. What is the order of the system? Let's count the dots. What's our highest dots in the first equation? Second, what's our highest dots in the second equation? 1, so in total it's third order. So this is a third order system because this is second order, this is first order. So in total it is third order. There is no acceleration because there's no mass. So that one's kind of a tricky one. I didn't really know at the beginning. It's okay to just kind of skip it and move on, but with these degrees of freedom, we have different sum of forces. I want to make sure we do that, so that's what's going on here. Third order system. Questions? Hey, just in this case, don't combine them. There's no way for us to combine this in a way that gives us a nice second order equation, anything like that. All right, what I want you to do is pull up your laptops. I want you to open MATLAB. We're going to be in Simscape, which is a part of Simulink. So you're going to start a new Simulink. As you're doing that, questions? Third order system. Yeah. Oh, great question. Yeah, why don't I put the Z2 over here? Because it's not actually the output. For this equation, for this one, Z1 is the output for the mass. That's its position. So in this case, Z2 is the input. So yeah, I just want to keep all the like terms, not necessarily put all the Z's together on the same side, but I want the Z1s. This is my output variable. Any other Z's are going to be my input. And again, why I don't combine these two is that I don't want a Z2 dot, so one output derivative variable, mixed in with another output, the Z1 double dot. So we can't just try to combine it all. We want to keep these separate. So this is my output side. Anything else, we should have no derivatives on the right-hand side, the input side. But yeah, good question. Good question. All right. Let's Any other last questions before I turn the page? Okay, we can't do a transfer function, by the way, because we don't have a single input, single output. I mean, I could do it for this one, but I could not do it for this one. So I'm just not going to do the transfer function. SimScape. Can we create a SimScape model? So you took the on-ramp. So in MATLAB, you do a new Simulink, and it'll ask you if you want to start with a template. So if you scroll down a little bit, or there's some drop downs, SimScape, this type of problem is a mechanical translational. So I always want to start with a template that makes sense. So we've got a template for mechanical translational. That's going to give you something that looks like this. So it's got a scope. It's got the solver. This will not run without the solver. It also gives you a ground, translational reference. This is basically your ground or your wall. There's a non-moving zero, everything. And then we've got a converter here. So I just want you to look around. There's the library browser. If you know what you're looking for, like mass, you can double click and just type in mass, and it'll pull up a mass for you. So if you know what you're looking for, you can just double click and type in stuff. Otherwise, you can use the library browser under SimScape, Foundation Library, Mechanical. There's a bunch of different elements, sensors, stuff like that. So I know you've all mastered it since you did the on-ramp. You all feel really great about it. But just humor me and try to do it. Or no, I can help you with that. What's going on? Do you have like MATLAB? Now you can do it on the online. If you have problems with your MATLAB on your computer, you can do the online version now. I wouldn't recommend it like for the whole entirety of this class, because it might not be able to do all the things we need it to do. But oh, you're stuck in online. You can't just like uninstall it all and download the newest version. Oh, okay. You just need to like wipe your computer. Oh, you already got it, and you got the node. I see. Oh, okay. So in the Foundation library, there's something called mechanical sensor. That's going to give you a displacement, so you can find a displacement sensor. You can also look for sources, mechanical sources. You can find a force source, and so by connecting it to the various things, we can actually get it to start moving. There you go. Oh, is it going? It's about ready to graduate. Yeah. So we know what these things are called. I mean, if you don't want to have to look through, you double click, you type in mass. You double click, you type in spring. You double click, you type in damper. Those are the terms that they use. And then you can connect it as such. Just make sure that the damper is connected to the ground. The harder part is, so some of you've got the three components. The harder part, and we don't need a node, by the way. You can just connect them. But we need an ideal force source. To be able to get this thing to move, I need an input. And so that would be under sources. And then we want a displacement center or sensor. That would be under the sensors. So most of what you need is in the library. So under mechanical, this has basically all the stuff that goes into any kind of translational system. Sensors, sources, elements. And they're very similar if I switch between translational, rotational. There's a lot of similarities. They connect the same way. They have a lot of similar themes. If you got questions, let me know. If, like, do you know how to connect them? You want to know? There's something called, I think, translational free something. You don't need it though. Yeah, you don't need it. You can just connect them because what we care about mostly in this problem is how the mass is going to move. So, but there is here translational elements. There is a free end. You could use it as a node if you want to. It's really not going to do anything. It's zero mass. Double click. Oh, what do I have here? Oh, wow. There's a lot. Oh, it doesn't matter. I mean, you can do it to make it look nice. It's fine, but that's not going to affect it. Let's see. You can. I've taught you some of the stuff. You can use Control R to rotate stuff if you want to connect it a little bit better. Oh, okay. You're getting close. You got a source. Oh, hello. Hey, we're making the Simscape. So you want to have an idea? What does a force source look like? Force source looks like. So this would be our. Oh wait, force source. And it's looking for a couple of things. B, S, R. Then we got our displacement sensor, which looks like. Wait, what kind of sensor is that? Yeah, that's good. All right, so we've got to have the elements. We've got to have what comes with the template. We need a force source, and we need a sensor, displacement sensor. Those are all listed under sensors and sources. Are you ready for me to show you mine? It's not like it looks great, but I've got all the important stuff. Okay, so here's what I have. Again, you don't need the node. I got my damper, I got my spring, I got my mass. This is the wall. So my source is going to provide a force. Now, anytime I'm dealing with C and R, basically every sensor and source has a C and R. C, you always want to ground. So both of the C's, I ground here. That's like our starting point, C. R is what we want to connect to what we want to read or what we want the force applied to. So for both of these blocks, I have the R connected to the mass. And the last thing I want to talk about is the converters here. So everything in green, this is part of Simscape. Simscape is nestled inside of Simulink. And so there are some things like if I want to use the scope is part of Simulink, but I have to convert it from the Simscape area using the converter, and then it can give me a readout right here. Same thing for my input. Simulink has a lot of different sources. They got step, they got ramp, they got all these different things. But to use it in Simscape, I have to convert it. So the Simscape converter takes those, it allows you to use other Simulink things either for the input or the output. That's what's going on here. So I'd like you to try to set this up, try to run it. For my input, I use the pulse generator. You can plug in any kind of source that you can get from the Simulink library, any Simulink source, you just give it some kind of force and see what the displacement is like. But I just want you to be able to run it because in homework 1, you have a very similar problem. So if you can get this to run, once you have a working model, you can save it as something else. You can adjust it a little bit. And that way, it's easier than just starting from scratch every time. Part of engineering is just saving files in a way that you remember what they are and putting them in right folders so you can find them. Wouldn't you say, how many of you have like thousands of emails in your inbox? Oh boy. 9,000 emails in your inbox. Okay, your personal email. Yeah. Wow, 9,000. Anyone else beat 9,000 emails, you think? That's crazy. I try to keep mine under 10. What? 10 in the inbox. What about the spam? What do you mean? You keep the spam? Okay, he beat you. 17,000 is a lot. If it's Gmail, they've probably been telling you for years, you got to upgrade. Things will be deleted. Uh-oh. Oh, no. 48,000 emails. In Gmail? How do you have the space for that? You must not have much on your drive. I don't know. Okay. You want the R for both these connected to the mast. C should be connected to ground for both blocks. Yeah, like that. Now, if there's a problem, MATLAB probably won't run. A lot of times it'll give you an error. Some errors that typically happen is like if either the C or the R ports are not connected to something, it's going to have problems. If this is not part of it, it's going to have problems. It needs a solver connected somewhere. It doesn't matter where it's connected in the system. It doesn't have to be connected to ground or anything. But now this sensor, if you notice, it has two outputs. It has velocity and position for displacement. So if I want to look at velocity, I can just connect it there. P is for position. So if I want to see the position of this, we can do it there. And you can also label things. So if you click on a block, it kind of shows the text. You can change it to text. So if you get to more complicated systems, you can label stuff. And I got one last, maybe, I think this can be a helpful block too to the workspace. So it can take your data and it can just spit out a big table in MATLAB, and you can take that and actually put in Excel, do some analysis of it, stuff like that. So that's also something that can be helpful for this class. I also want to say one thing that's also nice, if I want to track a bunch of things, if I want to see where the node's going, if I want to know what this force is at all times or anything like that, up at the top, once you run it, so once it's able to run, there's something called SimScape results. That's where you can look at everything. It graphs everything for you. You can pull up kind of any data from the whole system. So if I want to see the spring force over time, that's something that we can see. And the graphs are typically a little bit nicer. You can change the units. What units do you think this is in? This is displacement. The x-axis is time. It's always time. It is meters. This is meters. But do I know that? I mean, I have units, but it doesn't tell me meters. It's always going to be standard metric. So it is meters. Now, in SimScape results, when I'm done, I can change it to feet. I can change it to maybe inches and stuff. So, like, you can adjust some of the graphs depending on what you want to see. So that's what I've got on my next slide. Well, I guess I simplified this a little bit. So this is another way that it can look, but I still have the same pulse generator. I've got the solver. After I run it, I can look at the SimScape results, and this is where you can drop down and change it to different units. So the graph looks typically nicer, but I can look at the spring force. I can look at the force. I can look at, anything about the mass, displacement, velocity, acceleration, anything like that. That's all contained in the SimScape results. One other important thing is the stop time. So you can adjust how long this runs. It's always going to default to 10 seconds, but if it's not quite showing everything, then you can adjust the time. You can go to 20 seconds, 100 seconds, stuff like that. And then the last thing, if you're getting a graph that's really chunky, really blocky, like it's not smooth, this is how you can change it. So up in modeling, under model settings, you just do a drop down on solver details. You can change your max step size. So this happens, like this graph, it might be fine. It's just some where maybe it's more complicated systems. Sometimes it chooses a really large step time, and so you get a really blocky graph. So if you want something that's smooth, you adjust the max step size. That's how you can get a nice smooth graph. So that's under model settings, drop down right there. So I will post these slides as you're doing the homework. If you have a really blocky graph, it doesn't look good, these are some things that can help adjust it. So I'm just changing the step size so I can get a smoother output. But I'm going to go back. I'll just go to here. Basically, I want you to be able to run it. I want you to get a working result, because for the homework, you're going to have 2 different small SimScape ones. This one is almost just like this, it's just very similar. So I want you to be able to get this working so that for homework it's a little bit easier. And then once you're done with that, you can go. So I'll post these slides and I'll stop recording.